All right, so now we got parallel circuits. I want to clarify. I'm sure that looking at all that math for the series circuits was a bit complicated. It's hard to pick up, especially hard to pick up on just an online lecture. I'm sure. You're not going to have to do too much circuit math. There's going to be just maybe a bit on the homework, but mostly it's just going to be conceptual. So the key there from series circuits was that resistors in series, you add up the resistance. So the more resistors you have in series, the higher the resistance, the lower the current. So if you have, some Christmas lights with 4 bulbs, and of equal resistance, and then say you have that connected to a specific battery. So Christmas lights with 4 bulbs connected to a certain battery, we get some brightness. Then if you take a Christmas light, you replace that with a Christmas light that has 8 bulbs in series, connected to the same battery. So we have the same voltage being provided, but we have twice the resistance because we have 8 bulbs instead of 4 in series. So twice the resistance. So we're going to have half the current running through each bulb. That means that the brightness of each bulb is going to drop as well. And if we lose one of those bulbs, we lose them all, right? So how's parallel different? Let's look at that. And we'll probably do less math for this. So yeah. So first thing, when you have when you have a circuit in parallel, you get the same voltage drop across each branch as opposed to them dividing the voltage. So if we look back at our board, so here we can see our parallel circuit. We have our battery, which will still be 12 volts, but now the circuit is split into 2 different branches with a resistor in each. And let's say the resistors are the same, 2 ohms like before. What we find, if we look at this diagram here, so we have some initial current, right? This is the total amount of current in our wire, our circuit, and then that current hits some junction. When it hits this junction, it has to split. Some current will go through this branch, and some current will go through that branch. If the resistance in each branch is the same, then the current will split evenly. But regardless, what we find is this. If we call the initial current I1, if we call the current in this leg or this branch I2, and the current in this branch I3, we get this. I1 is equal to I2 plus I3. Furthermore, what we find is that the voltage drop across each is still 12 volts. That's what this first statement here, voltage is the same across each device, is saying. So we have a 12 volt drop across this resistor and 12 volts across this resistor. And that has to be true because, again, our current has to get to 0 volts before entering back into our battery. So it comes out at 12 volts, it splits, part of the current goes through this leg where it drops through 12 volts. And so once it gets to the other side, it's back at 0 and can get to the battery. Same for the current that goes through this leg, it has to drop through 12 volts before going back into the battery. The total current, so now let's look at number 2. The total current in the circuit divides among the parallel branches. The amount of current in each branch is inversely proportional to the resistance in the branch. So we saw that first part, right? The current has to split at that junction. Now, if our resistors are the same, then the currents will be the same. So if we have 2 ohms and 2 ohms, we'll get let's see, if we have so we have 2 ohms and 2 ohms. We won't go into the math, but we'll get the same amount of current in each one. If, let's say, instead we had 1 ohm on this leg and 2 ohms on that leg, then we'll have twice as much current in the 1 ohm leg than in the 2 ohm leg. And no matter what, it has to follow Ohm's law. Again, we're not going to go through every bit of the math, but just conceptually, so the current has to split. The splitting depends on the resistance, and the voltage drop is the same for every leg. And then number 3, the total current in the circuit equals the sum of the currents in all its parallel branches. So we saw that, right? You add up all the current in each branch, and that should give us the total. Now, if we look at 4 and 5, as the number of parallel branches increases, the overall resistance in the circuit is decreased. So that's interesting. What we're saying here is that as we add branches, we actually drop the resistance. So if we take our circuit here and here, let me just draw a new circuit. So what we find is this. If we go back to a 1 resistor circuit, right, and let's say this resistor has 2 ohms, then the total resistance in our circuit is 2 ohms. So 12 volts, a 12 volt battery with 2 total ohms will give us 6 amps. But now if we look at 2 ohm resistors in parallel, the resistance actually drops. We get more current. But we have more resistors, you ask. It should be higher. Well, think about it like this, right? The resistance depended on how easy or hard it is to transport current or electrons through a wire. And by adding a new leg, we now have 2 options or 2 ways for the electrons to make it through the wire, the circuit. So we're giving more pathways, and that drops the resistance. It makes it easier for this current to run through. And you can see it from the math. So for series circuits, resistors add up normally. So for series, well, I'll write it out. I'll write it out later. But for series, the resistors add up directly. For parallel, they add up inversely. We're not going to do it, so you don't need to worry. You don't need to see the math. But the point is, the more resistors in parallel, the less the resistance. So if I actually added a 3rd resistor here, the resistance would drop even less. Now, and then here's the good part about a parallel circuit. If you break one path or one element of the circuit, it doesn't interrupt the flow of charge in the other paths. So let's say we have our 3-leg circuit here. Let's say one of these breaks. Let's say this light bulb breaks or burns out. Instead of the current in all the legs going out, or in all the resistors going out, like in the series circuit, it only goes out in this leg. The current is still able to make it through these other 2 legs. And so if we think back to those Christmas lights, if we choose to make our Christmas lights so that all the light bulbs are in parallel with each other, one of those bulbs can go out and all the others would still light up. We're not going to lose it, which I assume is probably better when you're putting up Christmas lights. Now, in reality, I think a lot of the nicer Christmas lights will have multiple multiple light bulbs in series in parallel. So we'll have multiple legs, in other words, and each leg might have 5 or 6 light bulbs in series. But so if one of those goes out, that whole leg goes out, but then you have all the other legs or branches of your circuit as well. So when 2 identical lamps in a circuit are connected in parallel, the total resistance is less than the resistance of either lamp alone. Consider a lamp powered by a battery. Charge flows through both the battery and the lamp. It has to make it through both. It's a full circuit. So homes are often wired in parallel, or electrical equipment in homes. Your outlets in homes are wired in parallel. That way, if one device goes out or burns, we can still use the other ones, right? So if our toaster in this example goes out, our heater, our lamp will still work. But the thing is, the more devices we add in parallel, right, the lower the resistance. The lower the resistance, the higher the current. So using these parallel systems, it puts us at risk of getting very high currents, and that could cause a fire or something. So what we do is we use a fuse. So fuses are some wire that melt when the current gets too high. So it's maybe not made out of copper, but some other material that melts when the current is above what we want it to be. And if it melts, then the circuit breaks and there's no more current flowing through, and we could prevent a fire from starting. Nowadays, we don't use fuses like that. We have circuit breakers, but it's the same idea. So yeah, so that's it for this. So that's it for Electrodynamics, chapter 23. Again, shoot me an email if you guys have any questions. Be sure to finish the homework assignments for chapter 22 and 23. And I'll see you guys at the... I'm not going to see you, but everybody says on YouTube. You'll hear me in the next video.